Hi, Assalamualaikum, and see you again. And if, so, modeling a single neuron, and we'll see how is it. Okay. Okay. Let's first look at the what we call the McCulloch-Pitts model. Okay. McCulloch-Pitts model is one of the famous model for the single neuron. It's been established in 1957, okay, a long time ago. Until now, it's been revised quite depth and conclude a good way of representing the neuron. Okay, and the next slide, what we're gonna have is this one. Okay, so this is how the summary of McCulloch-Pitt model. So McCulloch-Pitt model basically a bit lengthy, but here I summarize in a short form. Okay, in so that it's easily understand. I skip the hardware part of the McCulloch-Pitt model and we go to the software part. How is implementation in the software part? Okay, look at here on the slide. Now we got a cell and recall back that we got a dendrite, we got a nucleus, seroma, cell body, and axon. And here we have synapse connect to the dendrite, the other neuron, and we're gonna sum up all the electric signal from all the synapse and pass over. So in this case, what the McCulloch-Pitt model summarize is like this. Okay, down there. Okay, so this is the McCulloch-Pitt model. So you're gonna see here this line, basically let's say this line, okay, dendrite, and this line is another dendrite, let's say, okay, and this line is another dendrite. All right, so we're gonna have that one, and this summation basically is inside there. Okay, yeah, okay, so this one, the yellow, and this one are the same. Okay, they're gonna sum up all together. All right, and the synapse, so this is synapse. Okay, wait, wait, and wait, and activating function, both of these, all of these three together are synapse. Okay, so that's how uh, McCulloch-Pitt model for the neuron. Okay, so I repeat it again. These three line, basically these are 1, 2, and 3. Basically you can imagine one dendrite, one dendrite, and one dendrite. You got 3 dendrite here, and the summation basically imitate this one. Okay, so you got some of the electrical signal, so basically this one. Okay, it sum all of the uh, electrical signal sum ups. Okay, and finally the synapse. So this is synapse and this is the synapse. So this synapse basically are modeled through the weight 2, and weight 3, as well as this function. This is a function. So these three, 1, 2, 3, represent synapse. Okay, that's in basically the general view of how neuron are being modeled into computer science. In other terms, how the neuron been modeled into being represented by a mathematical model. Okay, so this is how you see it. The single neuron has been modeled into mathematical model. Okay, now, and this is called threshold. Okay, above the threshold or below, setting the threshold, and we call it the activation function. Remember, so this one we call it the activation function, and this is a summation mean three of these will be summation. Let's move to the next slides. All right, okay, now this is what we have just now. Remember, we got you remember the weight and activation function. Active function and the weight are called activation function, and it become a threshold, and it represent the synapse, and this is the summation to represent the soma nucleus that sum all of the signal, and weight and these are threshold activation function or synapse, and this line basically represent the dendrite from the other neuron. So this is one neuron. So this is dendrite from other neuron. They pass over to the signal. So dendrite, in other words, this is an axon. Okay. Now with this one, what when you bit more detail, it's gonna be so. Let's say X the input. X is the input. Input mean, remember just now I said input are coming from your eyes, from your ears, listen, from your mouth, or from the other sense, skin, kidney, and all those things. So in this case, the input is in terms of numbers. Okay, everything can represent as numbers. Images can represent as numbers, and signal can represent as numbers, and so on. So this is the input from outside, from mouth, from what you see, from the sense, from the skin, sensor. Okay, sense. So the input are so consider a signal. So signal are go to the axon. Okay, now W is a weight. We call it a weight, and 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 S is called a summation. So this is the way how is it. You got a summation, you got an activation function with the weight, and you got axon. So basically you have S W multiplied by X plus B. Okay, and X the input. So now I see the input data from outside sources like sensor, skin, and so on. So W is weight. So this weight basically is this one. Okay, so this this one. Okay, weight. Okay, and this S means summation, which is this one. Okay, and this can represent as this summation. Okay, this is summation. So summation can be S equal to W multiplied by X plus B. Okay, so this W and B is considered synapse. Okay, represent the synapse, and you got there W is a weight. Okay, there, and B we call it a bias. Okay, bias. So the scientists put it B there, and then this is the output. So this is the output. Okay, so this is how is it been modeled. Okay, once again, so this is from previous slide summation. Wait, this is axon as a signal. This, the axon will be summation to all and has a weight and function, activation function and weight as a synapse. So we got an input and we got a dendrite axon and we got a weight there, weight and also the weight, and S is the summation and F, which is the activation function. Actually F is this activation function. So basically this one, okay. So when you put it S into the function, it will become the output. All right, so remember that X S equal to W multiplied by X, X multiplied by W, and then plus B, and then this S will use this function. This S gonna be, so this S put into the function. Okay, so okay, got it? Okay, I repeat back again. So this, the circle is a neuron. So this is considered a neuron. A circle is a neuron. And in computer science, we call it nodes. We can't call it neuron. Basically, people call it nodes. So for me, I call it neuron because when we call neuron, it's more clearer. So the neuron as the summation. So this is a summation. The summation S basically is equal to W multiple X plus B. And W is put it there next to the axon dendrite from the other input, signal on the input coming, and W is just next to the input. So W plus X, W multiplied by X and plus B. Okay, and S will be put into the function F. Insert into the function S gonna be the output. And here, if you see, so X is an input, this is a neuron, okay, and this is considered a nucleus soma where do the summation. And the synapse basically is the combination of W, B, and F. So you can play around with B, W, and F. Okay, so in this case, if you change F, it will change the value. If you change W, it's also going to change the output. If you change B, also change the output. So based on this function B and W, you can change the value become low, spike, or low. Okay, that basically, and so so this is one of the function of what is F. F basically is this is what we call a sigmoid function. Okay, you don't have to worry what this is the function all about. And if you see this function, basically this function stand at the end. Okay, so mean at the end, whatever S you got in here will be input to the function S, and this function S basically this one. And if you see, this is the use function normally used in artificial intelligence. And if you see this function, basically what it happened is, let me put in color. Okay, black. Okay, black. Okay, now basically here they put it 1. Okay, here is 0. Okay, now you see this is X, this is Y. Y FS, the output, X is the input. So if you see here, whatever the input, it doesn't matter the input, the output will between 0 and 1. If S is negative, okay, if S is negative, the value will be around here. And if X is positive, doesn't matter how many positive, the value of the output is always be 1. Okay, so this is basically terus tegak, terus okay, this forward. So this is the output. The output is 1. It doesn't matter what is the input here. Whatever the S from 0, 1, 2, 3, 4, 5, 6 until infinite, the output will be always 1. So I just make it 1. So that means fired or something like that. Okay, mean fired, spike is set into 1. So basically the Fs function is also important, as well as weight. Weight, you can put numbers there. Okay, hope you can catch up this one. We move to another slide. All right, now we look a bit more detail a bit. Okay, all right, now look here. Okay, see here. Okay, you got now 3 input. You got 3 axon there, 3 dendrite. So you got 3, 1, 2, 3. So you got 3, and then so mean if you got 3 mean you got 3 signal, electrical signal. In this case, signal can be data, any data. Okay, data. So 3 data represent these 3 dendrite, and you're gonna have a weight to each of these dendrite. Weight 1, weight 2 for this one, and weight 3 for this one. And you got the neuron. This is summation. This is the function Fs and the output. Now you look. Now look how the summation happen. Summation. So this is the summation. Okay, represent this one. Now look at the summation. S W1 multiple xy. W1 multiplied by x1 plus W2 multiplied by x2 plus x3 multiplied by W3, and then all together plus B. Okay, all together plus B. You see, so this is one, this is this, 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 plus this one, you plus all these 3. This is what we call summation. This notation mean this. We summation all of this. X1 multiple W1 plus X2 multiplied by W2 plus X3 multiplied by W3. Then all together plus B. Okay, so this S then will be moved into the function F. Fs become the output. So this one is this one, and this is the output then. Okay, so that's the way how you do it. Okay, so this is how you modeling the single neuron. Okay, and still far away from AI, you know. We'll come that moment later. This is we want to know how the single neuron been modeling into computer, into algorithm to be understood by computer. All right, and next slide. Okay, so this is the function just now. Play the similar role. Okay, now So basically, these are the summation of this. Okay, this what we call summation, and these are basically this one, and this also represent this one. Okay, you see wx plus wx, w1 plus x1 my plus w2 multiple x2 plus summation and so on until n. So 1 I is equal to 1, I is equal to 1, I 2, I 3. So in this case you got 3, so n is 3. So here is 3. Okay, so here is 3. If you so n mean you can have many 1, 2, 3, 4, 5, 6, 7 until n. In this case you got 3, so n is equal to 3. Okay, got it? All right, and let's move to the next slide. Let's look at the example. Okay, so the example here basically x, let's say x is equal to 1 and w is equal to 0.3 and b is, we said it, b is negative 0.1. Okay, now what is the formula just now? So this is the formula. So s summation wx multiple x plus b. So x is 1 multiple by x is 1 multiple to w is 0.3. So w multiple x, 1 multiple 0.3 equal to 1.3 plus b. Plus b. B is minus 0.1. So s will be 2.2. Okay. So this is 1.3 minus 0.1. Okay, so S will be 1.2 equal to 1.2. Okay, now S is 1.2 and S put into the function of f. And let's say the f function is fs. Whatever you put the function, the output is also the s, the same. So 1.2, put here fs, the function output is 0.2. So fs is 0.2 because I said it, this function is like this. If I set function the other thing, the output will different. So this one, to make it easy, I put the function fs is equal to itself s. Okay, so in this case s is 0.2, 1.2 s, and s put it into the function f, and fs is equal to s, so s equal to s. So fs is 1.2. So this is the way how the neuron work. Okay, so this is the best way to imitate how the neuron work. Okay, with the dendrite and all those things. Now let's see another one. Okay, so in this case the same just now, but the most important is, let's say, okay, example here, let's say x is called alphabet. Okay, this is a not, let's say this is a statement that x is an alphabet. Oh, yes, x is alphabet. We know it is alphabet because we are human. See, this is x. If you take this photo with your handphone and let the software and know what is this, it's going to be difficult for the software. And we have to tell the software that basically x is called the alphabet. So these x are called the alphabet. Okay. So this is input here, and when I said X is called alphabet, so I'm going to introduce you one term, say target value or label. So in that case, where X is called alphabet, in other words, X is labeled as alphabet. Remember? Okay, so X is labeled alphabet. So this is especially is alphabet. The target value or the label is called alphabet. If you say that alphabet is 1, non-alphabet is 0, so this must be equal to 1. Okay, so now you see X is labeled to 1. Okay, 1 represent alphabet. If it is 1 is alphabet, it is with 0 mean non-alphabet. Okay, so in here, since X is alphabet, so X I label it as a 1, mean it is alphabet. Okay, so let put this way. Now the target value, let me, okay, when you got the target value, I need to introduce you another term called loss. You lost, hilang. Okay, hilang. I lost something. I lost my dog. Lost, hilang. So hilang mean target value, this value minus fs, minus this one. This is fs. So target value minus fs. Okay. So when you minus it, target value minus fs, and the result, whatever the value it is, target value minus fs, it is called loss. And loss must be 0. And loss must be 0. So target value minus fs must be 0. The target must be 0. Okay, the target must be 0. Now, let's see. X is labeled as x1. So x is the input. The target value is 1. 1 is considered alphabet. Okay, uh, because it called alphabet. Okay. Now, let's say x is 1 and it is 1.2. Okay. So in this case, the loss basically is need to be the loss need to be 0. Okay. Now in this case, if you calculate, okay, the target value just now is equal to 1. Okay, target value equal to 1. 1 is alphabet 1 because X is called alphabet. X, picture X is called alphabet. Picture X is called alphabet. So target value is 1. Now target value is 1. Now you got 1 here. Minus Fs. You have calculated Fs 1.2. 1.2 is equal to what? Minus 0.2. Okay, right? Minus 0.2. So in this case, as you know, the loss must be 0. So this is not 0. The loss must be 0. This is not 0. Okay, less than 0. I need a 0. So what you do? In this case, what we need to do, what we call it, this, when you're moving forward direction, you need to repeat it back again. So when we repeat back again, I need to moving backward. The target must be 0, but I don't have 0.
and repeat back again. And this time, the synapse play a role, okay, to let the threshold, because the only changing is the synapse. And synapse basically represent by W and W and function S, function F. So this W, this B, and this Fs is the synapse. So I'm going to change. Let's say I'm going to change this is negative 0.3. Okay, I change this negative 0.1. I change it. I delete this one. I put it 0.3. Now, now you target. Now it moving forward back. Now, if you change this b equal to negative 0.3, then we moving forward again. Now we calculate x multiple w 0.3 minus plus b. B is negative, so we got here the new value fs become 1.3 plus minus 0.3. So I have 1. Okay, and fs seem the same, so I got 1, and you got 1. Okay, now back to here. So I'm gonna, so now the target value is 1. I repeat it back again. Okay, I second round. Okay, so the target value is 1 here. Target value label is 1. 1 minus fs. Fs is 1. 1. So is equal to 0. Now you see, loss must be 0. Now loss is equal to 0. Now I got loss is 0. Then in this case, my neuron is perfect. In this case, X is called alphabet. My neuron will be with this value. W is basically 0.3. So F S is equal to S, and B is negative 0.3. Okay, so this is how you do it. So basically, in the case of X, image X is called alphabet. X is called alphabet. In this case, my neuron W will be 0.3, B will be negative 0.3, and function Fs is S. So this is the setup for X is called alphabet. And I think it's okay with you, this one. And next slide is modeling network of neuron. Never mind. We're gonna stop here. Let you relook back my pre-recorded lecture and get digest and understand it. Okay. If you don't understand, just let me know on WhatsApp. Okay. Thank you very much.